In the twilight of the 19th century, the world of physics seemed almost complete. Scientists believed they had uncovered nearly every secret the universe had to offer. Newton's mechanics described motion and gravity with perfect precision. Maxwell's equations united electricity and magnetism into a single elegant theory of electromagnetism, and thermodynamics revealed the laws of heat and energy. Many physicists felt that the great age of discovery was over. What remained, they thought, were only a few minor details to polish, like adding the final brushstrokes to an already finished masterpiece. Yet, hidden in those very details was a problem so small and yet so profound that it would shatter the classical worldview entirely. This problem was known as the mystery of black body radiation. Imagine a perfect furnace, one that absorbs every bit of radiation that enters it and emits light, depending solely on its temperature. This ideal object, which scientists called a black body, fascinated physicists because it represented the purest form of thermal radiation, radiation unspoiled by material imperfections or chemical composition. If they could understand how such a body radiated energy, they believed they would uncover the fundamental laws governing all light and heat, and so began one of the most important quests in the history of science. In laboratories across Europe, physicists heated metal cavities to different temperatures, allowing them to glow, first a dull red, then bright orange, and finally a blinding white as the temperature increased. They measured the intensity of light emitted at different wavelengths, from infrared to ultraviolet. The pattern was clear: as temperature rose, the body emitted more energy, and the peak of that emission shifted toward shorter wavelengths. But when scientists tried to explain this pattern using the classical theories of the day, the laws of thermodynamics and electromagnetism, something went terribly wrong. The equations predicted that at short wavelengths, especially in the ultraviolet range, the emitted energy should grow without limit. If that were true, every warm object, even you and I, would emit infinite energy in the form of ultraviolet light. Clearly, that was impossible. This absurd result became known as the ultraviolet catastrophe. For decades, physicists wrestled with this paradox. The most brilliant minds, Lord Rayleigh, James Jeans, Wilhelm Wien, proposed theories and mathematical expressions to match experimental data. Each attempt brought partial success, but ultimately failed to explain the full radiation spectrum. The problem seemed simple, yet it defied every principle of classical physics. It was as if nature herself was whispering that something in their understanding was incomplete. At the heart of the puzzle was the question, how does energy behave when emitted by matter? According to classical physics, energy could vary continuously, like a smooth flow of water. There were no limits or steps. Any amount was possible. But the experimental results from black body radiation didn't agree. The measured curve of emitted energy dropped sharply at high frequencies, contradicting the predictions of classical theory. No matter how physicists adjusted their equations, reality refused to fit the mathematics. By the late 1890s, the situation had become desperate. The industrial age had given scientists powerful tools, spectrometers, precision thermometers, and new methods to heat and measure light. But even with all this progress, the theory lagged behind. It was as if humanity had built telescopes strong enough to see the stars, but lacked the language to describe them. In the prestigious universities of Berlin, Munich, and London, physicists debated endlessly, searching for the hidden truth behind radiation. Among these thinkers was a reserved but determined German scientist named Max Planck. He was not a revolutionary by nature. In fact, Planck valued order and classical reasoning. To him, the laws of physics were timeless and unbreakable. But as he turned his attention to the radiation problem, he began to sense that he was standing at the edge of something extraordinary. Planck believed deeply in the power of mathematics to reveal nature's harmony, and he devoted himself to finding an equation that could bridge the gap between theory and experiment. Before Planck's involvement, Wilhelm Wien had proposed a formula that seemed promising. His Wien's law described the radiation spectrum quite well at high frequencies but failed at lower ones. Later, Lord Rayleigh and James Jeans introduced another approach based on classical assumptions. Their equation matched experimental data at low frequencies but exploded into infinity at high ones, the ultraviolet catastrophe again. Neither model worked across the full range of wavelengths. The mystery deepened. Two theories, each partially correct, stood on opposite sides of a chasm that no one could yet cross. To understand why this problem was so difficult, one must imagine the mindset of physicists at the time. Classical physics viewed energy as continuous, something that could be divided endlessly. Light waves, according to Maxwell, were oscillations in the electromagnetic field, spreading smoothly through space. Temperature, according to thermodynamics, represented the average energy of vibrating particles. There was no room in this picture for abrupt changes or discrete packets. The very idea of energy being chunked into tiny indivisible amounts seemed absurd. Yet, it was precisely this assumption that would soon unlock the puzzle. In 1899, Planck decided to tackle the problem using statistical methods, a field pioneered by Ludwig Boltzmann, another German physicist. Boltzmann had introduced the idea that the behavior of systems could be described statistically by considering the probabilities of various microscopic states. Planck initially disliked Boltzmann's probabilistic approach because it seemed to abandon the deterministic beauty of classical physics. But the black body problem forced him to reconsider. With great reluctance, he adopted Boltzmann's reasoning, hoping to find a bridge between energy and entropy that could explain radiation. In his calculations, Planck imagined the walls of a black body as being filled with tiny oscillators, little entities that could vibrate at specific frequencies, absorbing and emitting electromagnetic energy. He tried to derive how much energy these oscillators should contain at a given temperature to match experimental results. After endless nights of calculation, he realized something astonishing. If he assumed that these oscillators could only possess energy in discrete amounts proportional to their frequency, his equation matched the experimental curve perfectly. Mathematically, he expressed it as eta neben, where n is an integer, nu is the frequency, and h is a constant of proportionality. That constant, now called Planck's constant, turned out to be one of the most important numbers in science. At first, Planck did not grasp the full implications of what he had done. He considered his quantization assumption a mere mathematical trick, a clever way to make the formula fit the data. He didn't believe that energy was truly quantized in reality. Yet, his equation worked with astonishing accuracy across all wavelengths. The ultraviolet catastrophe vanished. The spectral curve aligned beautifully with experimental results. Nature, it seemed, had accepted Planck's gamble. This was the beginning of the quantum revolution, though Planck himself didn't yet realize it. The black body radiation problem, which had once seemed a minor detail, had forced physics into a new and unfamiliar territory. The continuous world of Newton and Maxwell was giving way to a granular universe, where energy came in discrete packets. Quanta. What started as an effort to understand how objects glow, when heated, ended up revealing that nature itself operates by a set of laws deeper and stranger than anyone had imagined. As the news of Planck's solution spread, the scientific community reacted with a mix of admiration and disbelief. His formula was undeniably correct, yet its underlying assumption, that energy is quantized, seemed physically nonsensical. To many, it felt like a mathematical trick rather than a real description of the universe. But slowly, experimental evidence began to accumulate, showing that Planck's trick was more than mathematics, it was reality. The black body radiation problem had revealed the limits of classical physics. It was as if humanity had been staring at the smooth surface of a lake, believing it to be continuous, only to discover it was made of countless tiny drops. The implications went beyond radiation. They hinted at a fundamental discreteness in the fabric of energy itself. It would take years, and the work of other great minds like Einstein, Bohr, and Schrödinger, to unravel the full meaning of Planck's discovery, but the spark had been lit. The quantum age had begun, born from the ashes of the ultraviolet catastrophe. Even in its earliest form, the black body mystery carried a poetic irony. It was light itself, the very symbol of clarity, that exposed the darkness of human understanding. The phenomenon that seemed most familiar, the glow of heat and color, turned out to conceal the deepest secret of the universe. Planck's persistence in studying it marked one of the greatest acts of scientific courage, the willingness to question the unquestionable, to break from tradition when reason demanded it. In the laboratories of Berlin, Planck's name began to spread quietly. His discovery didn't immediately revolutionize the world, but it planted a seed. It challenged a generation of thinkers to reconsider what energy, matter, and even reality truly were. The mystery of black body radiation, once a technical nuisance, had become the gateway to a new understanding of the cosmos. And though the 19th century had prided itself on the completeness of its physics, the century that followed would be defined by its dismantling, by the birth of the quantum universe. Planck's journey began with a simple question: why do heated objects glow the way they do? But in pursuing that question, he uncovered a truth that changed science forever. The black body problem wasn't just about light or heat. It was about the limits of human knowledge, the boundary where the known dissolves into the unknown. The same glowing furnaces that lit the laboratories of the 19th century became the beacons guiding humanity toward a new vision of reality. And so, as the 20th century dawned, the mystery of black body radiation stood resolved in one sense but open in another. The equations were complete, yet their meaning was only beginning to unfold. The world had glimpsed the first hint of a quantum reality, a world where certainty faded, where probabilities ruled, and where even the smallest quantum of energy could alter the course of history. As the echoes of the 19th century faded, a quiet revolution began to stir in the halls of European science. Max Planck's law of radiation had solved one of physics' most stubborn problems, but in doing so, it had whispered a message that few were ready to hear. The elegant equations of classical physics had been fractured. The seamless flow of energy, once thought to be continuous, now appeared to come in indivisible bursts. Quanta. To Planck, it was a mathematical compromise. To the next generation, it would become the foundation of a new reality. At first, few understood the depth of what Planck had proposed. Even he viewed the quantization of energy as an abstract concept, a temporary stepping stone, not a permanent truth. He believed that, someday, a more refined version of classical physics would restore continuity and harmony. Yet, as experiments grew more precise, nature refused to cooperate with classical expectations. The universe seemed to favor Planck's strange arithmetic of quanta over the smooth calculus of the past. The black body radiation problem, which had begun as a simple question about how objects emit heat and light, now stood at the gateway to a revolution in physics. The formula worked flawlessly, but no one could fully explain why. This paradox unsettled the scientific community. It was as if someone had discovered a bridge that perfectly connected two cliffs, but didn't understand the laws that kept it standing. The bridge held firm, but its foundations were invisible. Planck's constant, h, became the mysterious symbol of that hidden truth, a key that fit a lock no one had seen before. In the early years of the 20th century, physics found itself divided between faith in the old and curiosity for the new. Some clung to the deterministic beauty of classical laws, where every event had a cause and every motion a predictable outcome. Others, drawn by the strange accuracy of Planck's formula, began to suspect that the world operated according to deeper principles, rules that defied intuition. It was in this atmosphere of tension and transformation that a young patent clerk in Switzerland, Albert Einstein, took Planck's idea one step further. Einstein's insight came from studying another enigma, the photoelectric effect. When light shone on certain metals, it ejected electrons. Classical physics predicted that increasing the brightness of the light should increase the energy of the emitted electrons. But experiments showed the opposite. It wasn't brightness, but frequency. The color of the light. That mattered. Low-frequency light, no matter how intense, couldn't knock electrons free. Only high-frequency light, like ultraviolet, could do so. This defied all classical logic. Einstein proposed a bold solution. What if Planck's quanta of energy weren't just mathematical tricks, but real physical entities? What if light itself consisted of discrete packets of energy, what we now call photons, each carrying an energy equal to Planck's constant times its frequency? With this idea, Einstein transformed Planck's hesitant step into a giant leap. Suddenly, the behavior of light, heat, and radiation began to make sense. The photoelectric effect, once a riddle, became a triumph of the quantum idea. At first, even Planck resisted Einstein's interpretation. The notion that light could be both a wave and a particle was too radical. It seemed to violate everything known about electromagnetism. Waves and particles were supposed to belong to different worlds, one continuous, one discrete. Yet experiment after experiment confirmed Einstein's reasoning. Reality, it turned out, didn't care about human preference for simplicity. Nature had chosen duality. Light was both wave and particle, depending on how one looked at it. The black body radiation mystery had unleashed a chain reaction. What began as a problem of glowing furnaces had evolved into a redefinition of energy itself. By quantizing energy, Planck had cracked open the door to quantum theory. Einstein's photons pushed that door wide open, and as the years passed, more discoveries followed. The atomic spectra, the structure of the atom, the strange dance of electrons around nuclei. Each of these phenomena seemed to follow rules that defied classical explanation, but made perfect sense when viewed through the lens of Planck's quanta. Meanwhile, Planck himself remained both proud and uneasy. He recognized the importance of his discovery, but he viewed the quantum as a necessary evil, a provisional hypothesis that explained the data but lacked physical clarity. He continued to hope that someday a deeper, continuous theory would emerge to replace it. Yet, as he grew older, the evidence piled higher, and the world moved forward without waiting for his comfort. The black body radiation problem had started a revolution that no one, not even its founder, could stop. In the decades that followed, the quantum idea spread like wildfire. Niels Bohr used it to build his model of the atom in 1913, describing electrons orbiting nuclei in quantized energy levels. When an electron jumped from one level to another, it emitted or absorbed a photon with an energy exactly matching the difference. A direct consequence of Planck's formula. Bohr's model explained the mysterious lines in the hydrogen spectrum, a triumph that confirmed the power of quantum thinking. Soon, others joined the quantum quest. Werner Heisenberg, Erwin Schrödinger, and Paul Dirac developed new mathematical frameworks, quantum mechanics and wave mechanics, to describe the microscopic world. What Planck had introduced as a desperate fix became the foundation of a new scientific language. The laws of nature, once thought to be smooth and continuous, revealed themselves as discrete and probabilistic. Certainty gave way to probability, and the universe began to look less like a clock and more like a symphony of possibilities. But to truly understand the magnitude of this transformation, one must return to where it all began, the black body furnace. In that simple, glowing cavity lay the first glimpse of quantum reality. When physicists measured its spectrum, they weren't just studying heat, they were peering into the architecture of the cosmos. Every point on that radiation curve represented a dialogue between energy and matter, a whisper from the quantum world beneath. Planck's constant, so small that it seemed almost meaningless, turned out to govern everything, from the behavior of atoms to the color of the stars. The implications extended far beyond theory. The quantization of energy became the foundation of modern technology. Every laser, every LED, every transistor, every quantum computer owes its existence to Planck's work. Even the very screens through which people now learn about Planck's story, the glowing pixels that emit specific frequencies of light, are living testaments to the mystery of black body radiation. What once puzzled 19th century physicists has become the invisible engine of the 21st century world. Yet, there is a deeper, almost philosophical beauty in this story. The mystery of black body radiation is not just about science. It's about the nature of discovery itself. It reminds us that the greatest breakthroughs often arise from the smallest cracks in understanding. Planck did not set out to create quantum physics. He sought only to fix a problem in classical thermodynamics. But by daring to question the familiar, he revealed a deeper truth that the universe is layered, complex, and often counterintuitive. Progress in science, as in life, often begins with admitting what we don't know. The story also carries a touch of tragedy and humility. Planck's later years were marked by personal loss. The destruction of his home during World War II, the execution of his son by the Nazi regime, and the turmoil that swept through Germany. Yet even in his darkest moments, he held on to the belief that truth, once discovered, transcends human suffering. For him, physics was not merely a profession. It was a moral calling, a quest to understand the laws that govern all creation. The same quiet persistence that drove him to solve the black body puzzle also guided him through the storms of his life. When Planck received the Nobel Prize in 1918, it was recognition not just of a formula but of a revolution. The Nobel Committee honored him, in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. But few at that moment could grasp how far-reaching his discovery truly was. The concept of quantization would go on to redefine chemistry, electronics, and even our understanding of time and space. It would give rise to the atomic bomb, quantum computing, and the theory of everything physicists still chase today. Every scientific revolution begins with a question. For Planck, it was a question about the color of heat, why a glowing object changes hue as its temperature rises. The answer, as it turned out, was a doorway to the fundamental workings of the universe. In solving one small riddle, he opened 1,000 others. The mystery of black body radiation became the seed from which modern physics grew, proving that sometimes the smallest anomalies contain the greatest truths. Even now, over a century later, scientists and philosophers return to that moment in 1900, when Max Planck stood before the German Physical Society and presented his equation for black body radiation. His audience listened politely, unaware that they were witnessing the birth of a new era. In that simple, measured presentation, the age of classical certainty ended, and the age of quantum reality began. The ripple from that moment spread across time, shaping everything from the atom to the cosmos. Today, we can trace the light of every star, the energy of every atom, back to the mystery that puzzled Planck. The glow of a candle, the radiation of the sun, the hum of a microwave oven, all are expressions of the same universal law he discovered. The invisible constant H governs them all, silently binding the universe in its quantized rhythm. Every photon of light, every vibration of energy, every wave that dances through space, carries the signature of Planck's insight. And so, the story of black body radiation is more than a tale of physics. It is a testament to human curiosity, the relentless drive to understand the unknown. From the darkened laboratories of the 19th century to the quantum technologies of today, the spirit of discovery burns with the same flame that once glowed in Planck's furnaces. What began as a mystery of light became the illumination of knowledge itself. In the end, the puzzle that once defied the greatest minds of the 19th century became the key to unlocking the 20th, and the centuries that would follow. Planck's journey, from confusion to revelation, mirrors the journey of science itself, a passage through uncertainty toward deeper truth. His discovery reminds us that even when the universe refuses to obey our expectations, it still offers its secrets to those who listen closely enough. The black body radiation that once puzzled the world now stands as the first note in the grand symphony of quantum reality, a song that continues to echo through time, guiding humanity ever closer to understanding the infinite. At the dawn of the 20th century, science stood on the edge of an unseen transformation. The great pillars of classical physics, Newton's laws, Maxwell's equations, and the principles of thermodynamics, seemed unshakable. The universe, as scientists then believed, was a vast machine operating with perfect predictability. Every motion, every vibration, every pulse of energy could be traced back to a cause, calculated, and understood. But behind the comforting order of these laws, cracks were beginning to form. Nature was hiding something extraordinary, waiting for a mind daring enough to see beyond the known. That mind was Max Planck. Planck was not the kind of man one would expect to lead a scientific revolution. He was reserved, methodical, and deeply loyal to the classical ideals of physics. He believed the universe was rational and harmonious, ruled by laws that could be expressed with mathematical precision. To him, the beauty of physics lay in its certainty, the belief that every phenomenon, from the fall of an apple to the glow of a star, could be explained by continuous, predictable equations. But destiny had other plans for him. It was precisely this devotion to precision that would lead him to question the very foundation of continuity itself. In 1899, Planck was studying a seemingly simple but stubborn problem: how objects emit radiation when heated. Scientists had been measuring the light emitted by heated bodies, so-called black bodies, and recording the intensity of radiation across various wavelengths. The data revealed a clear pattern. As temperature increased, the peak of radiation shifted to shorter wavelengths. Yet when physicists tried to describe this with existing laws, the equations failed miserably. The classical theories predicted that at higher frequencies, radiation intensity would grow infinitely. A physical impossibility. The mystery was more than a mathematical puzzle, it was a direct challenge to the heart of physics. Planck knew that if this problem could be solved, it would not only explain how light and heat behave but also unify thermodynamics and electromagnetism. For years he worked tirelessly, adjusting equations, exploring every possible theoretical path, but nothing fit. Then, in an act of intellectual desperation and brilliance, Planck did something completely unorthodox. He broke one of physics' most sacred assumptions. He proposed that energy was not emitted or absorbed continuously, but in discrete amounts, or quanta. This single idea changed everything. The concept was radical, almost heretical. Until that moment, scientists believed that energy, like water, could flow in any amount, no matter how small. But Planck suggested that nature had a smallest possible unit of energy, like individual drops that could not be divided further. Mathematically, he expressed this as etalum, where E is energy, null nu is frequency, and H is a new constant, now known as Planck's constant. This number, though unimaginably small, represented a fundamental scale of reality. It was as if the universe itself pulsed with a hidden rhythm, a quantized beat that underlay all creation. At first, Planck did not realize the revolutionary power of what he had done. He viewed quantization merely as a mathematical trick, a convenient fiction that allowed his formula to fit the experimental data. But behind those numbers lay a truth far greater than even he imagined. His formula perfectly described the spectrum of black body radiation, something no one before him had achieved. When compared to real experimental results, the match was flawless. Planck had done what many thought impossible. He had reconciled theory with observation, bridging the gap between the known and the mysterious. Yet, the world of science was not ready to accept such an idea. The notion that energy existed in indivisible packets defied centuries of thinking. It challenged the continuous waves of Maxwell's electromagnetism, the smooth flow of thermal energy in thermodynamics, and the very logic of classical physics. The universe, it seemed, was not the unbroken fabric scientists had believed it to be. It was granular, made of discrete steps, like a staircase rather than a ramp. For Planck, this realization was deeply unsettling. He was a man who cherished continuity, and his heart resisted what his mind had discovered. But the evidence was undeniable. The equations worked only when energy was quantized. With humility and precision, Planck presented his findings to the German Physical Society on December 14, 1900. In that moment, often described as the birth of quantum physics, the world changed, though few recognized it then. The audience that day likely saw Planck's talk as another incremental advance in thermodynamics. But history would remember it as a turning point, the moment when physics took its first step into the quantum realm. What began as a simple attempt to explain how objects glow with heat became a gateway to understanding the very building blocks of reality. To appreciate the depth of Planck's concept, one must understand what quantization really means. Imagine light not as a continuous wave of energy, but as a series of tiny pulses, each pulse carrying a precise amount of energy, determined by its frequency. The higher the frequency, the greater the energy of each pulse. This meant that nature itself had a built-in limit, a smallest possible packet of energy that could not be divided further. In essence, Planck had discovered the atomic structure of energy. Just as matter was composed of atoms, energy too was composed of quanta. The implications were staggering. If energy was quantized, then perhaps all physical processes, from the vibration of atoms to the radiation of stars, operated in discrete steps. The smooth, predictable world of Newton began to dissolve into a world of jumps and probabilities. But Planck was cautious. He did not claim to have redefined physics, he only offered a formula that worked. He famously said, "I did not seek to revolutionize physics. I was merely trying to explain black body radiation." Yet revolutions often begin this way, not with intent, but with necessity. In his small office in Berlin, surrounded by notebooks and mathematical tables, Planck must have sensed that he was touching something profound. His constant, h though tiny, became the thread that connected the seen and unseen. It was the scale at which classical physics broke down and the quantum world began. To most of his contemporaries, this number seemed insignificant. But in time, h would be recognized as the cornerstone of modern science, appearing in every quantum equation, from the behavior of electrons in atoms to the energy of particles in the cosmos. In the years that followed, Planck continued refining his theory, but his cautious approach left room for others to push it further. Einstein in 1905 extended Planck's idea to light itself, proposing that electromagnetic radiation was composed of quanta, later called photons. That bold interpretation transformed Planck's cautious hypothesis into a full-fledged theory of quantum reality. Planck's discovery had opened the door, Einstein walked through it. But in those early years, Planck's concept of energy quanta stood alone, strange, controversial, and ahead of its time. Many physicists resisted it, arguing that it violated the very essence of physical law. Some dismissed it as a temporary fix, a mathematical convenience. Yet, as more experiments confirmed its accuracy, resistance began to crumble. Quantum theory was no longer an idea, it was a necessity. Nature itself demanded it. What made Planck's concept so revolutionary was its universality. It wasn't just a theory about radiation. It was a window into the structure of the universe. Every atom, every molecule, every beam of light followed the same rule. Energy came in discrete packets. From the glow of a star to the flicker of a candle, everything operated under the rhythm of quantization. The world that seemed continuous to the human eye was, at its core, a mosaic of quanta. The beauty of Planck's discovery lies not only in its scientific brilliance, but in its philosophical depth. His concept of energy quanta reshaped how humanity perceives reality. It forced scientists to accept that nature might not conform to our expectations of smoothness and order. It revealed a universe where the smallest scales behaved differently from the macroscopic world we experience. The comforting predictability of classical physics gave way to a strange, probabilistic realm, one where uncertainty, chance, and quantum leaps rule. For Planck, this realization carried both wonder and discomfort. He was a man of logic and discipline, not rebellion. Yet his discovery forced him to become the father of a revolution he never intended to start. As he once said, "A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die, and a new generation grows up that is familiar with it. His words reflected the slow acceptance of his theory, a truth too radical for many to grasp immediately. Still, history has a way of honoring those who listen when the universe whispers. Planck's introduction of the quantum concept was not just a milestone in physics, it was a shift in human thought. It marked the end of an era of certainty and the beginning of a journey into the unknown. The mystery of light and heat had led humanity to a deeper mystery, that the universe itself might be built upon indivisible packets of energy, vibrating to a cosmic rhythm that even now we struggle to fully understand. The legacy of that moment still resonates today. From lasers to quantum computers, from atomic clocks to the very theories that describe the birth of the universe, Planck's quanta are everywhere. The digital world we live in, where information is measured in bits and energy in discrete states, is the modern echo of Planck's insight. He may have introduced quanta to solve a narrow problem, but he ended up introducing humanity to the architecture of existence itself. In those quiet winter nights of 1900, when Planck worked by lamplight over his calculations, he could not have imagined the world his discovery would create. He only sought to bring harmony between theory and experiment. But in doing so, he redefined harmony itself, from a continuous melody to a symphony of quantized notes. The concept of energy quanta became the foundation upon which the edifice of modern physics was built. And though Planck remained humble, history remembers him as the man who turned a paradox into a principle, a puzzle into a revolution, and a question into a doorway to the quantum world. As the 20th century dawned, the scientific world was unknowingly standing at the edge of a revolution that would redefine reality itself. The concept that Max Planck had dared to propose, that energy is emitted and absorbed in discrete packets called quanta, had begun to ripple through the consciousness of the world's brightest minds. Yet, even Planck himself could not fully grasp the depth of what he had unleashed. To him, it was merely a desperate attempt to make sense of experimental data that stubbornly refused to fit the classical mold. But nature had revealed one of her deepest secrets, and humanity would never see light, matter, or even existence the same way again. In the months and years following his 1900 paper, Planck's work spread slowly but steadily through the scientific community. His law of black body radiation had provided the first mathematical description that perfectly matched experimental observations. But the true meaning behind his formula puzzled even him. Energy quantization was not something Planck believed in as a physical reality, at least not yet. To him, it was a purely formal assumption, a necessary fiction to save the laws of thermodynamics from collapse. But in this fiction lay a hidden truth waiting to be discovered. Science often advances not because its pioneers see the whole picture, but because they dare to take a single, uncertain step into the dark. As laboratories across Europe began testing his equations, the evidence continued to support his conclusions. The quanta were not disappearing, their traces could be seen in every heated filament, every glowing ember, and every starlit night. Still, many scientists refused to accept the notion. To suggest that energy, that most fundamental and continuous of physical quantities, came in indivisible lumps was a direct challenge to the smooth, deterministic universe that Newton and Maxwell had built. For centuries, physics had been a realm of continuity, of elegant curves and predictable motion. Planck's quanta shattered that illusion, introducing abruptness into a world that had always seemed seamless. It was Albert Einstein, only a few years later, who would see the true significance of Planck's strange assumption. In 1905, Einstein took Planck's quantum hypothesis and applied it to light itself, proposing that light was made of particles, later called photons. This bold leap transformed Planck's mathematical fix into a physical reality. Suddenly, the universe was no longer continuous but grainy, built from discrete units of energy. Einstein's paper on the photoelectric effect demonstrated that light could knock electrons out of metal, only when its frequency reached a specific threshold, regardless of intensity. This could only be explained if light itself came in quantized packets. Planck had unknowingly lit a fuse, and Einstein's spark ignited it into the blazing fire of quantum physics. The reactions within the scientific community were as diverse as they were intense. Some dismissed these ideas as absurd, calling them mathematical trickery. Others, sensing a profound shift, began to explore this strange new frontier. Among them were pioneers like Niels Bohr, who would use Planck's constant to describe how electrons orbit atomic nuclei in quantized energy levels, and later Werner Heisenberg and Erwin Schrödinger, who would turn quantum theory into a full-fledged description of the microscopic world. The seed that Planck had planted in 1900 was now growing into a forest of revolutionary thought. But while others embraced the radical implications of his discovery, Planck himself remained cautious, almost reluctant to abandon the comfort of classical physics. He once confessed that a new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die. Planck had seen firsthand how deeply entrenched the old ideas were. He too had been raised in the classical tradition, molded by the determinism of Newton and the continuity of Maxwell. To imagine that the universe worked in sudden, indivisible jumps was unsettling even to him. Yet, as experiments accumulated and theory evolved, he came to accept what his own mathematics had revealed: nature herself was quantized. The building blocks of reality did not flow like smooth rivers. They came in pulses, discrete and indivisible, like the notes of a symphony played on the scale of the cosmos. Over time, Planck's quantum concept became the cornerstone of modern physics. His constant, the now famous H, found its way into every major equation that defined the behavior of atoms, light and energy. It became a universal fingerprint of the quantum world, appearing in Schrödinger's wave equation, Heisenberg's uncertainty principle, and even in Einstein's theory of relativity through the study of light-matter interactions. What had begun as a mathematical curiosity was now the foundation of reality itself. Every quantum leap, every photon, every atomic transition whispered the same truth: that Planck had touched upon the deepest rhythm of the universe. Yet the story of Planck's Quanta was not just one of science, it was also one of philosophy and faith in human understanding. Planck was not a radical by nature. He was a conservative thinker, deeply devoted to the ideals of order, logic, and harmony in the universe. His revolutionary idea came not from rebellion, but from a relentless loyalty to empirical truth. When theory and observation collided, he chose truth over tradition. That quiet act of intellectual courage became a model for generations of scientists. The quantum theory did not just rewrite equations, it reshaped how humanity perceived reality itself. Suddenly, certainty gave way to probability, and the universe became a place of infinite mystery. As the years passed, the implications of Planck's idea began to reach beyond physics into chemistry, electronics, and eventually into the very technology that shapes modern life. The understanding that energy is quantized led directly to the development of semiconductors, the transistor, and the computer age. Lasers, fiber optics, and even the smartphone in every hand are descendants of that one idea. Every time an LED light glows, or a satellite transmits information across space, Planck's quanta are at work. It is as though his discovery, born from the quiet study of glowing metals, now pulses through the veins of human civilization. In his later years, Planck reflected often on the strange path his work had taken. He had lived through wars, seen his homeland rise and fall, and witnessed the transformation of science beyond anything he could have imagined. Through all of it, his belief in the harmony of the natural world never wavered. To him, science was not merely the pursuit of knowledge, but an act of reverence, a way to glimpse the divine order behind the chaos. He once said, "Science cannot solve the ultimate mystery of nature, and that is because, in the last analysis, we ourselves are part of the mystery that we are trying to solve." Those words capture the humility of a man who discovered something that changed everything, yet still saw himself as a seeker, not a conqueror. The acceptance of Planck's quantum concept marked a turning point in the human quest for understanding. It bridged the known and the unknown, linking the tangible world of measurement with the invisible dance of atoms and light. His work showed that even in the smallest scales of existence, nature follows her own logic, one that defies human intuition yet upholds perfect consistency. It is a logic that governs not only the heat of stars but the flicker of neurons, the bonds of molecules, and the energy that sustains life itself. To understand Planck's quanta is to recognize that the universe speaks in a language of discrete possibilities, where every event, every interaction is a step in a cosmic dance of energy exchange. By the time Planck received the Nobel Prize in 1918, the world had already begun to feel the tremors of the quantum revolution. The Great War had ravaged Europe, and yet amid the destruction, science offered a vision of something eternal, a truth beyond human conflict. As Planck stood to receive his award, it was not just a personal triumph, but a symbolic moment for all of physics. The universe had revealed one of its deepest principles, and the torch of discovery had been passed to a new generation of explorers. They would carry Planck's idea into the heart of atoms, across the vastness of galaxies, and into the technologies that define our age. And so, the story of Max Planck's energy quanta is more than a tale of scientific discovery. It is a story of how human curiosity can pierce the veil of the unknown. It shows that even when one begins in doubt, driven only by the desire to solve a stubborn puzzle, one might stumble upon the architecture of the cosmos. Planck's quanta remind us that reality is layered, that beneath the continuous lies the discrete, beneath certainty lies mystery, and beneath knowledge lies wonder. Every photon that lights our world, every spark that powers our machines, is a tribute to the quiet genius who first glimpsed the quantized rhythm of creation. The revolution that began in Planck's study continues to echo across the frontiers of science. In quantum computing, information itself is treated as quanta, bits that exist in multiple states at once. In quantum cryptography, the very principles of Planck's theory guard the secrets of the digital age. Even in cosmology, where scientists seek to understand the birth of the universe, Planck's constant defines the smallest scales of space and time. It is as if his discovery carved a bridge between the microscopic and the cosmic, showing that the same laws govern the dance of electrons and the birth of galaxies. In every sense, his revolutionary concept of energy quanta has become the language through which we understand existence. When the lights dim and we look at the night sky, what we see, every glimmer of starlight, every shimmer of cosmic energy, carries the fingerprint of Planck's quanta. Each photon traveling across the vastness of space tells a story that began over a century ago in a small Berlin laboratory, where one man, driven by persistence and intellect, dared to question the continuous and discovered the discrete. From that moment, humanity stepped into a new era, the quantum era, and nothing was ever the same again. In the grand halls of scientific thought, where Newton's laws had reigned supreme for centuries and Maxwell's equations had woven light and electricity into one majestic theory, there arose a quiet tremor, an idea so small, so radical, that it would shake the very foundations of classical physics. That idea was Max Planck's quantum hypothesis. It began as a whisper among equations, a mathematical fix to a stubborn problem about how objects emitted heat and light. But the whisper grew louder until it became the sound of revolution. It was not just a challenge to old theories, it was a challenge to the very way humanity understood nature. A rupture between the continuous and the discrete, between certainty and probability, between the predictable and the unknowable. For centuries, classical physics had painted the universe as a grand, harmonious machine. Every motion, every flicker of energy could be predicted with enough knowledge and precision. The equations of Newton, Maxwell, and Boltzmann described a world of order, a cosmos governed by continuity and determinism. To the physicists of the late 19th century, The dream was almost complete. The structure of atoms, the movement of planets, the behavior of gases and light, all seemed to fit within a unified framework. Only a few minor puzzles remained, anomalies that most scientists believed would soon be solved within the familiar laws of nature. Yet, in the quiet laboratories of Berlin, Max Planck saw something that refused to obey. The problem of black body radiation was not new, but it was persistent. When physicists heated objects and measured the light they emitted, the results did not match theory. According to classical physics, energy should increase infinitely as the wavelength shortened, a prediction that defied reality. Nature, in her infinite wisdom, refused to explode into infinite energy. The data revealed a curve that rose, peaked, and then fell. No classical formula could explain it. For years, Planck wrestled with this puzzle, trying every possible mathematical adjustment. But no matter how carefully he tuned his equations, the mismatch remained. It was as though nature was guarding a secret, one that could only be revealed by breaking the rules. And so, in 1900, Planck made a move that defied the very essence of classical thought. He proposed that energy was not continuous but came in discrete packets, quanta. Each quantum, he suggested, was proportional to the frequency of radiation, with the constant of proportionality being what we now call Planck's constant, h. This was not a minor correction, it was a declaration that the universe itself might be built from indivisible steps of energy. It was as if he had taken the smooth surface of the classical world and revealed that beneath it lay a staircase. No physicist before him had dared to imagine such a thing. The assumption seemed almost unthinkable. How could light, which flows in waves, also come in tiny chunks? But Planck's formula matched the data perfectly. The riddle of black body radiation was solved, at a cost. The price was the comfort of classical continuity. When Planck presented his results to the German Physical Society in December of 1900, the room was filled with curiosity but also disbelief. The equations were elegant, but the interpretation was disturbing. Energy, quantized. The very notion contradicted centuries of physics. To the minds of that era, it was as radical as claiming that time flowed in jumps or that space itself was made of grains. Yet the evidence was undeniable. Planck's law fit every experimental measurement like a glove. The simplicity of the solution hinted at a deeper truth, a truth that physics had not yet dared to confront. At first, Planck himself resisted the implications of his own hypothesis. He treated it as a mathematical trick, a tool to patch the failure of existing theories. He did not intend to rewrite physics, only to reconcile it with observation. But the universe does not care for human intentions. The more scientists explored his idea, the more they realized it was not a trick but a revelation. The quantum hypothesis had cracked open the door to a new realm of physics, one where energy, matter, and even causality behaved in ways that defied classical expectations. It was a world of probabilities, not certainties, of sudden leaps, not smooth transitions. The classical machine had been replaced by a quantum orchestra, playing a melody that only mathematics could fully hear. Einstein was one of the first to recognize the power of Planck's idea. In 1905, he extended the quantum concept to light itself, proposing that light was composed of particles, quanta of electromagnetic radiation, later known as photons. This proposal directly challenged Maxwell's theory of continuous electromagnetic waves. It was a daring leap, and it worked. Einstein used Planck's quanta to explain the photoelectric effect, the observation that light could eject electrons from metal only if it reached a certain frequency, no matter how intense the light was. This could not be explained by classical wave theory, which predicted that increasing intensity should always increase energy. But if light came in quantized packets, each carrying a discrete amount of energy proportional to its frequency, then only photons above a certain threshold could free an electron. The puzzle was solved, and in doing so, Einstein gave physical meaning to Planck's abstract hypothesis. The scientific world was stunned. For the first time, two of physics' greatest pillars, Maxwell's electromagnetic theory and Newtonian mechanics faced a contradiction that could not be resolved within their own framework. The wave-particle duality of light was born, a paradox that would haunt and inspire generations of scientists. Was light a wave, or was it a particle? Planck's hypothesis said it could be both, depending on how one looked. It was a truth that classical physics could neither explain nor accept. The universe, it seemed, had a dual nature that defied human logic. By introducing the quantum hypothesis, Planck had unknowingly launched a revolution that questioned everything physics stood for. The idea that energy levels could be quantized meant that not all energies were possible, only specific, discrete ones. This struck at the very heart of classical theory, which assumed that all values were continuous. Suddenly, the smooth, predictable universe of Newton and Maxwell gave way to a world governed by discontinuity. Even time and motion began to lose their certainty. The comforting notion that knowing a system's present state could determine its future was beginning to unravel. It was not just a scientific upheaval, it was a philosophical one. Classical physics had been built upon determinism, the idea that the universe operated like a clockwork, its future entirely determined by its past. But Planck's hypothesis introduced randomness, or at least discreteness, into this picture. If energy could only change in jumps, then something in nature was fundamentally unpredictable. The universe was no longer an unbroken continuum but a dance of discrete steps. For scientists raised in the deterministic era, this was a profound shock. It felt as if the very fabric of reason had been torn. Planck's own feelings toward his discovery were deeply conflicted. He had immense respect for the classical tradition, for the symmetry and order that Newtonian physics represented. Yet, he could not ignore the truth revealed by his equations. He once said that, "My unshakable faith in the rational order of the universe has been confirmed by my discovery," even though that discovery contradicted the smooth rationality of classical mechanics. To him, truth was sacred, even if it meant dismantling the very structure of thought he had grown up with. This blend of intellectual courage and humility defined his role in the story of modern physics. As word of his hypothesis spread, new thinkers emerged who saw its potential. Niels Bohr applied Planck's ideas to the structure of the atom, proposing that electrons could orbit the nucleus only in quantized energy levels. This model explained why atoms emitted light at specific frequencies, something classical physics had failed to describe. When an electron jumped from one orbit to another, it emitted or absorbed a photon with energy equal to the difference between the levels, exactly as Planck's formula predicted. Once again, the universe had confirmed the quantum hypothesis. Every spectrum line from hydrogen to helium became a silent testimony to the truth of Planck's daring idea. By the second decade of the 20th century, the cracks in classical physics had widened into deep fissures. The old framework could no longer contain the new discoveries. The stability of atoms, the emission of radiation, the nature of heat, all demanded explanations that classical theory could not provide. Planck's hypothesis had become the bridge between two worlds, one fading, one emerging. The age of classical certainty was giving way to the age of quantum possibility. And yet, the transition was not easy. Many of the great physicists of the time resisted the change. They clung to the familiar logic of continuity, reluctant to embrace a universe built on discrete steps and probabilistic events. But reality is not bound by human preference. The quantum hypothesis continued to prove itself in every experiment, every observation. It was as if the universe itself had spoken through Planck's mathematics, revealing that beneath the apparent smoothness of existence lies a granular truth, a universe not of waves alone, but of quanta dancing in rhythm. Planck's challenge to classical physics was not born from rebellion but from necessity. He had not sought to destroy the old order, he had simply followed the evidence where it led. In doing so, he had redefined what science could be. His hypothesis forced physicists to look beyond appearances, to question assumptions once thought sacred, and to accept that nature's behavior might be stranger than any human model. The legacy of that challenge would echo through every future discovery, from relativity to quantum mechanics, from atomic theory to modern cosmology. In that moment of quiet defiance, in that decision to let truth outweigh tradition, Planck had not just solved a problem, he had changed the very language of science. The ripple that began with Planck's hypothesis did not stop at a single experiment or equation. It spread like shockwaves through the intellectual bedrock of science. Classical physics had been more than a body of knowledge. It was a worldview, a philosophy of certainty. To the great physicists of the 19th century, the universe was a vast, predictable machine. If one knew the position and velocity of every particle, the future could be calculated precisely, like the ticking of a perfect clock. That faith in determinism gave scientists confidence that nothing lay beyond reason. But Planck's idea of energy quanta struck at the heart of that belief, introducing a universe where the smallest actions occurred in sudden, indivisible jumps where continuity gave way to mystery. In laboratories across Europe, physicists began to test the strange implications of quantization. Each new experiment seemed to confirm Planck's law and, with it, the unsettling notion that energy flowed not as a smooth stream, but in discrete bursts. The ultraviolet catastrophe had been tamed, but at a cost. The old picture of nature was crumbling. The comforting equations of classical mechanics could describe the motion of planets, the swing of pendulums, and the flow of water, yet they could not explain why light left the surface of a hot metal or how atoms emitted their distinct spectral colors. The world beneath the microscope followed rules alien to human intuition. It was as though a hidden layer of reality had been uncovered, a layer that laughed at classical expectations. Einstein's interpretation of Planck's work deepened the fracture. His proposal that light itself consisted of quanta, later called photons, challenged James Clerk Maxwell's elegant field theory. Maxwell had unified electricity, magnetism, and light into a single continuous wave phenomenon. It was one of the crown jewels of 19th century science. To suggest that light came in packets seemed almost sacrilegious. Yet Einstein's explanation of the photoelectric effect was undeniable. Light below a certain frequency, no matter how intense, could not eject electrons. Above that frequency, even a faint beam could. It was a direct, empirical signature of quantization. Planck's constant, that tiny number first introduced as a mathematical convenience, had become the key to unlocking the energy of each photon. Classical physics could only watch as its seamless fabric began to tear. The resistance among older scientists was fierce. Many refused to accept the new language of quanta. They argued that the discontinuities were merely artifacts, temporary scaffolds that would eventually be replaced by smoother theories. Planck himself sympathized with their discomfort. He had built his career upon the principles of thermodynamics, upon the conviction that nature was continuous and calculable. Yet, paradoxically, it was his own work that forced him to abandon that belief. As years passed, and as experiments multiplied, the evidence became overwhelming. Nature did not obey the comforting smoothness of calculus alone. Somewhere, deep in its structure, the universe leapt rather than flowed. Niels Bohr's model of the atom gave the next great blow to classical thinking. Building on Planck's quantization, Bohr proposed that electrons orbit the nucleus only in specific energy levels. They could not spiral gradually inward, as classical electrodynamics predicted, because that would require the emission of energy in a continuous stream. Instead, electrons could exist only in certain allowed orbits, and when they jumped between them, they absorbed or emitted a photon whose energy equaled the difference between the levels. The spectral lines of hydrogen, those mysterious bright streaks observed through a prism, suddenly made sense. Each line was the signature of a quantum leap. Classical physics, which had no room for such abrupt transitions, could only bow to the new reality. The challenge grew even deeper with the rise of quantum mechanics in the 1920s. Werner Heisenberg's matrix mechanics and Erwin Schrödinger's wave mechanics though mathematically different, both rested on Planck's original insight. Energy levels were quantized. They described a world in which particles behaved like waves and waves behaved like particles, a world where certainty dissolved into probability. Heisenberg's uncertainty principle declared that one could never know both the position and momentum of a particle with infinite precision. The act of measurement itself changed the system being measured. For classical physicists, this was heresy. But for those who followed Planck's trail, it was revelation. The quantum hypothesis had not only challenged classical physics, it had exposed its limitations, revealing that the universe was not a clockwork, but a symphony of possibilities. Planck watched this transformation with a mixture of pride and unease. He admired the brilliance of the younger generation, Einstein, Bohr, Heisenberg, Schrödinger, yet he struggled to accept the philosophical implications of their work. He believed that the laws of physics should reflect order and necessity, not chance. Quantum mechanics, with its probabilistic nature, seemed to deny that order. Still, he recognized that the mathematical results were undeniable. Truth, however uncomfortable, was still truth. The revolution he had sparked had grown beyond his control, yet he continued to guide it with his quiet integrity. He once said, "The man who cannot occasionally imagine the impossible is not truly capable of discovering the truth." In his humility lay the strength of a pioneer who dared to contradict his own instincts in the name of knowledge. As the decades unfolded, the consequences of Planck's challenge permeated every branch of science. Chemistry found new explanations for the structure of molecules. Solid-state physics uncovered the quantum behavior of electrons inside crystals, leading to the invention of transistors and semiconductors. The theory of radiation paved the way for lasers and modern communication. What had begun as an abstract adjustment to explain the glow of heated objects had become the foundation of an entire technological civilization. Each discovery, each invention, whispered back through time to that moment when Planck divided energy into quanta. The universe, once thought to move in smooth waves, now pulsed in rhythms set by his constant. But the deeper philosophical challenge remained. Classical physics had promised certainty. If we knew the initial conditions, we could predict the future. Quantum physics replaced certainty with probability, declaring that nature itself was fundamentally indeterminate. For some, this was liberation, the end of mechanical fatalism. For others, it was disquieting, a blow to the idea of a perfectly rational cosmos. Planck stood between these worlds, bridging the age of determinism and the age of uncertainty. His hypothesis was the fault line upon which modern thought divided. The human desire for absolute knowledge had met the limits of measurability. In the years following World War I, as Europe struggled with devastation, science offered both hope and reflection. Planck, by then an elder statesman of physics, was revered for his contributions, but also for his moral strength. He had endured personal tragedy, the loss of children, the destruction of his home. Yet his faith in truth and reason never faltered. He saw in the quantum revolution not chaos, but deeper order, one that transcended human comprehension. To him, the apparent randomness of quantum events was merely a reflection of our limited perspective. There remained, he believed, a hidden harmony behind the veil. His challenge to classical physics was therefore not a rejection of order, but a step toward a higher one. A recognition that the universe's music was more intricate than the old instruments could play. The implications of that challenge continued to unfold long after Planck's lifetime. In the mid-20th century, quantum field theory emerged, marrying the principles of relativity with the quantum framework. Planck's constant appeared everywhere, in the interactions of particles, in the energy fluctuations of empty space, in the radiation of black holes predicted by Hawking. Each new equation bore his signature, each discovery echoed his insight. Classical physics had not been destroyed, it had been absorbed, reinterpreted as a special case within a grander quantum reality. The challenge had become the cornerstone. To the modern mind, raised on digital technology and atomic theory, The idea of quantization feels almost natural, yet one must remember how radical it once was. To break from continuity was to challenge the very notion of causality that had defined science since Galileo. Planck's courage lay not only in his intellect, but in his willingness to trust mathematics over intuition. He showed that truth may hide where reason hesitates to look. His hypothesis did not simply alter equations, it transformed our relationship with reality. The world became less mechanical and more mysterious, less certain yet more profound. Even today, as physicists probe the quantum realm with colossal machines and delicate detectors, the echoes of Planck's challenge resound. Each experiment at CERN, each quantum computer qubit, each entangled photon is a direct descendant of that first step away from classical certainty. The questions remain vast and unresolved. Is the universe ultimately continuous or discrete? Do the laws of quantum mechanics represent the final truth, or a doorway to something deeper still? Whatever the answers may be, the journey began with Planck's daring leap at the dawn of the 20th century. In the final measure, Max Planck's quantum hypothesis did more than challenge classical physics. It redefined human understanding. It taught us that nature is not obliged to conform to our expectations. It taught us that progress often comes not from defending old beliefs, but from daring to question them. In the glow of a black body radiator, Planck glimpsed a fragment of the cosmos's secret architecture, and from that fragment a new universe was born. One where particles are waves, where observation shapes reality, where existence itself vibrates in quanta of energy. The smooth clockwork of the 19th century gave way to the shimmering uncertainty of the 20th, and through that transformation, science found its modern soul. When we look back upon that moment in 1900, when Planck first presented his formula, it seems almost mythic, the instant when light itself confessed that it was not continuous. The quiet German physicist could not have foreseen how his modest assumption would echo through time, altering not just physics but philosophy, technology, and the very way humanity perceives its place in the cosmos. His challenge to classical physics was not an act of destruction but of creation, the birth of quantum reality. From that point onward, the universe was no longer a machine to be wound, but a mystery to be understood in probabilities and patterns, in flashes and leaps of unimaginable precision. The story of Max Planck reminds us that revolutions often begin not with thunder, but with silence. The silence of a man at his desk, staring at numbers that refuse to fit, daring to imagine that perhaps the universe itself plays by different rules. In that act of imagination, classical physics met its greatest challenger, and the modern world was born. Max Planck's journey into the mystery of black body radiation reached its defining moment when he introduced his revolutionary formula, an equation that would not only solve one of physics' greatest puzzles, but also open the gateway to quantum theory. The problem had haunted scientists for decades. When an object was heated, it emitted light that changed color with temperature, from a dull red to a brilliant white, but classical physics could not explain why. According to the theories of the time, as frequency increased, the energy radiated by the object should rise endlessly, leading to what was called the ultraviolet catastrophe. But nature refused to obey those predictions. Experiments clearly showed that energy emissions peaked at a certain point and then declined. Something fundamental was missing in the understanding of how light and energy interacted. Planck, a man known for his discipline and humility, was not seeking a revolution. He simply wanted to fit the data, to make the laws of physics consistent with experimental reality. He examined the behavior of electromagnetic radiation in a heated cavity, known as a black body, and searched for a formula that would match the observed results. Through careful thought, he derived an equation that perfectly fit the data across all frequencies. It was a triumph of precision, but behind this elegant success lay a shocking implication. To make the equation work, Planck had to assume that energy was not emitted continuously but in small, indivisible packets. Each packet was proportional to its frequency by a constant that would soon bear his name: Planck's constant. When he presented his findings in 1900 to the German Physical Society, few realized that the foundation of physics had just shifted. Planck himself regarded his assumption as a mathematical trick, not a statement about the real world. Yet his formula worked flawlessly. The mysterious spectrum of black body radiation was described with breathtaking accuracy, from the deepest infrared to the farthest ultraviolet. What classical physics had failed to explain, Planck's formula captured effortlessly. The invisible boundaries of energy that he had proposed matched the very rhythm of nature's light. This success brought both awe and confusion. How could something so strange, so contrary to centuries of understanding, fit reality so perfectly? The classical view imagined energy as a smooth, continuous wave, like ripples on a pond. But Planck's equation said energy came in discrete steps, like the notes of a piano rather than a gliding tone. Each frequency of radiation corresponded to a specific quantum of energy, and the higher the frequency, the larger the quantum. Nature, it seemed, spoke in integers rather than decimals. For physicists who had devoted their lives to the idea of continuity, Planck's formula was both beautiful and terrifying. It worked so well that it could not be ignored, yet its implications shattered their worldview. Among those who saw its potential was a young Albert Einstein, who would later use Planck's quantization idea to explain the photoelectric effect, proving that light itself behaved like a stream of particles. What Planck had discovered by necessity, Einstein would embrace as reality. The black body radiation problem had thus become the cradle of a new science. Planck's formula, simple in appearance, contained within it the seed of the quantum revolution. Its success demonstrated that nature's laws might not always conform to human intuition. The universe, in its deepest structure, behaved according to principles that were discrete, probabilistic, and strange. From that moment, physics would never be the same. Planck's accurate description of black body radiation was more than an achievement of mathematics. It was the moment humanity began to see beyond the visible spectrum into the secret architecture of the cosmos. His equation bridged experiment and theory, linking the glowing light of matter to the quantized dance of energy itself. It marked the end of the classical age and the dawn of the quantum world, a world where certainty dissolved into probability, and light, once thought continuous, revealed its hidden, pulsing rhythm. Planck could not have known that his modest pursuit of a formula would redefine the boundaries of science. Yet his discovery became the cornerstone upon which modern physics was built, from quantum mechanics to atomic energy, from lasers to computer chips. The curve that once puzzled the greatest minds now stands as a symbol of humanity's capacity to see the invisible. Max Planck's formula did not just describe black body radiation, it described the beginning of a new reality. When Max Planck introduced his concept of quantized energy, he could not have foreseen how profoundly it would reshape science and human thought. The fifth keynote, his Nobel Prize and the recognition of his discovery, marks not just an award, but the formal acknowledgement of a revolution in understanding. In 1918, Planck received the Nobel Prize in Physics for his work on energy quanta, a discovery that had begun quietly, almost reluctantly, and grown into one of the greatest intellectual transformations in history. His formula for black body radiation had forced the scientific world to accept that energy did not flow in a smooth, continuous stream but in discrete packets called quanta. This simple but radical idea would forever change the way we perceive light, matter, and the structure of the universe. By the time Planck was honored, the storm he had unleashed had already swept through physics. Einstein's explanation of the photoelectric effect, Bohr's model of the atom, and the emerging field of quantum mechanics all traced their roots to that one daring assumption. The scientific community finally began to grasp the magnitude of what Planck had done. He had cracked open a doorway into the subatomic world, a place governed by strange and unpredictable laws, where probability replaced certainty and waves became particles. The Nobel Prize recognized not just a single formula, but the birth of a new science, a science that would define the 20th century. Planck's reaction to this recognition was humble. He never saw himself as a revolutionary. He was a man of tradition, of discipline, and of quiet faith in the order of nature. He once remarked that he had no desire to found a new physics, but rather to explain the facts as they appeared. Yet his name had become synonymous with a new worldview. When he stood to receive the Nobel medal, the world saw not only a scholar but a symbol of change, a man whose insight bridged the gap between the classical and the quantum realms. His discovery had united theory and experiment, intuition and observation in a harmony that redefined science itself. In his Nobel lecture, Planck reflected on the meaning of his discovery. He spoke not of personal triumph, but of the deeper mystery of nature's laws. He emphasized that science advances not by the stubborn defense of old beliefs, but by the willingness to question them. His calm voice carried the weight of truth born from patience and struggle. The energy quanta, he explained, were not mere mathematical curiosities. They represented a fundamental property of the universe, woven into the fabric of radiation and matter alike. To him, this revelation was as much philosophical as scientific. It spoke of limits, of humility before nature's complexity, and of the eternal quest to understand creation. The world around Planck was changing rapidly. Europe was emerging from the First World War, and amidst the chaos, science remained a beacon of hope. The Nobel Prize brought a rare moment of unity and inspiration, reminding humanity that knowledge could transcend conflict. Planck's discovery symbolized the light of understanding breaking through the darkness of uncertainty. It showed that even the smallest ideas, a mathematical constant, a subtle adjustment to theory, could shift the course of civilization. Though Planck was celebrated, he remained deeply modest. He often credited those who built upon his work: Einstein, Bohr, Schrödinger, and Heisenberg. To him, the Nobel Prize was not the end of a journey, but a milestone in a collective effort to uncover truth. He continued to teach, to write, and to reflect on the philosophical implications of the quantum world. While others sought to exploit quantum theory for technological advances, Planck's mind lingered on its spiritual and moral meaning. He believed that beneath the apparent randomness of the microscopic world lay an unshakable order, a harmony too profound for human minds to fully grasp. In later years, as new discoveries emerged and quantum mechanics evolved into a vast and intricate framework, Planck's legacy grew even greater. The Nobel recognition became not just a personal honor but a symbol of the birth of modern physics. Every quantum equation, every atom of light and matter studied in laboratories around the world bore his influence. His constant, h, became one of the most fundamental quantities in nature, a bridge between energy and frequency, between the visible and the invisible. Planck's Nobel journey reminds us that revolutions often begin in silence, in the solitary persistence of one mind seeking order in chaos. The light that burns in every scientific discovery was kindled by thinkers like him, who dared to ask questions that others feared to face. His Nobel Prize did not mark the end of a problem solved, but the beginning of a deeper mystery unveiled. The mystery of the quantum world, where certainty fades and imagination takes flight. Max Planck's recognition was more than a celebration of science. It was the acknowledgement that humanity had stepped into a new era, guided by the courage to see the universe not as it seemed, but as it truly is. The sixth keynote in Max Planck's remarkable journey captures the deep and lasting impact his discovery had on the world of physics and beyond. His introduction of the quantum idea did not merely explain one scientific puzzle. It transformed the foundation of all science and changed how humanity understood reality itself. After Planck's revolutionary work, physics could no longer be confined to the predictable laws of Newton or the smooth waves of Maxwell's electromagnetism. A new universe had emerged, one that was mysterious, mathematical, and strangely beautiful, governed by probabilities and sudden jumps rather than by certainty and continuity. The influence of Planck's ideas spread rapidly across Europe and the scientific world. Young physicists, inspired by his discovery, began exploring the hidden patterns of the atom and the nature of energy. Niels Bohr used Planck's constant to design his atomic model, describing how electrons could occupy only specific orbits around the nucleus, leaping from one to another in quantum jumps. Albert Einstein built on Planck's work to explain the photoelectric effect, proving that light behaved like particles called photons. Later, Schrödinger and Heisenberg developed full theories of quantum mechanics, providing the mathematical language to describe this strange, probabilistic reality. None of this could have existed without Planck's first step into the unknown. The influence of quantum theory soon reached far beyond academic physics. It became the backbone of modern technology. Transistors, lasers, computers, smartphones, and even medical imaging all emerged from the principles first hinted at in Planck's black body radiation formula. The quantum world that once seemed abstract and philosophical became practical and essential, shaping the way humans lived, communicated, and explored. Planck's constant, once a mysterious symbol in an obscure equation, now defines the scales of energy that make up our digital and technological age. Every beam of laser light, every microchip, every satellite signal carries the silent echo of Planck's insight. But the impact of his discovery was not only scientific, it was deeply philosophical. Before Planck, scientists believed that nature could be completely explained through continuous, deterministic laws. Every effect had a cause, and the future was predictable if one only knew the present conditions. Planck's discovery shattered that illusion. The quantum universe revealed a world governed not by certainty but by chance, where observation itself affected reality, and where matter and energy were two faces of the same mystery. This new understanding forced philosophers and scientists alike to reconsider the very nature of existence, knowledge, and truth. For Planck himself, the journey was both inspiring and unsettling. He was a man rooted in classical traditions, who valued harmony and order, yet his discovery had unleashed a theory that embraced uncertainty and probability. He accepted it reluctantly at first, but gradually came to see its profound significance. In his later writings, he often reflected on the unity between science and philosophy, reason and faith. He believed that the ultimate goal of science was not merely to control nature, but to understand it with reverence. His quantum theory, he said, showed that beneath the apparent chaos of the microscopic world lay an elegant and purposeful order, one that reflected a deeper intelligence in the universe. Planck's impact also extended through his mentorship and his moral strength during difficult times. He supported young scientists who would go on to shape modern physics, and even as political and social turmoil engulfed Europe, he remained committed to the pursuit of truth. His calm authority guided a generation that would navigate the explosive growth of quantum theory. Through him, science learned not only new equations but also new values: humility before nature's mysteries, persistence in the face of doubt, and faith in the power of reason to reveal the unknown. Today, Planck's influence continues to define our scientific worldview. The Planck constant remains a cornerstone of modern physics, appearing in the equations of quantum mechanics, thermodynamics, and even cosmology. The very scale of the universe is measured in Planck units, the smallest possible lengths, times, and energies that define the structure of spacetime itself. His name lives on not just in textbooks, but in the fundamental language of reality. Whenever physicists explore the behavior of subatomic particles or the first moments after the Big Bang, they do so through concepts born from his discovery. The impact of Max Planck's work reaches into every field of science and every corner of human thought. It represents the moment when humankind realized that reality is deeper and more complex than the senses can perceive. It marked the birth of a new age of knowledge, where imagination and mathematics together could reveal truths beyond intuition. Planck's discovery was not simply a correction to classical physics. It was the creation of an entirely new vision of the universe. In the quiet glow of a heated metal, Max Planck saw something that others could not: the whisper of quantized energy, the hidden rhythm of the cosmos. His insight bridged the gap between the visible and the invisible, between certainty and possibility. More than a century later, his legacy continues to guide scientists as they probe the smallest particles and the vastness of space. The impact of his discovery endures as both a scientific triumph and a testament to human curiosity. The reminder that even the smallest idea, born in the mind of a single thinker, can change the destiny of the world. Max Planck's legacy did not end with the discovery of the quantum. It lived on through the transformation of science and the generations of thinkers who followed in his footsteps. The seventh keynote, his enduring influence on modern physics, marks the culmination of a journey that began with a simple question about the color of glowing light and ended with the reshaping of humanity's understanding of the universe. More than a century after his first paper, Planck's ideas continue to echo through every field of physics, from the quantum mechanics that governs the smallest particles to the cosmology that explores the vastness of space, time itself. His legacy is not just that he solved a scientific problem, it is that he opened a door that will never again be closed. The framework that arose from Planck's discovery became the foundation of 20th and 21st century physics. His constant, the tiny symbol, h, found its way into every fundamental equation that describes reality. It defines the energy of photons, the uncertainty of particles, and even the scale at which space and time lose their classical meaning. Without Planck's constant, the equations of quantum mechanics would be meaningless. It is the thread that connects Einstein's relativity to Schrödinger's wave mechanics, Heisenberg's uncertainty principle, and even the modern theories that seek to unite quantum mechanics with gravity. Through his work, the invisible fabric of reality gained its first true measure, a unit that marks the boundary between the known and the unknown. Planck's influence also extended through the generations of physicists he inspired. His ideas lit the spark that guided Einstein, Bohr, Heisenberg, and Dirac, who built the great structure of quantum theory upon the foundation he laid. Every major discovery of modern physics traces its lineage back to his insight: the structure of atoms, the behavior of semiconductors, the workings of lasers, the principles of nuclear energy, and the very functioning of the stars. Even the cosmic microwave background, the faint afterglow of the Big Bang, can be understood through the same black body radiation law that Planck derived in 1900. His discovery not only changed physics, it connected the smallest and largest scales of existence, uniting the quantum and the cosmic in one continuous story of energy and light. Yet Planck's legacy was not confined to scientific equations alone. He embodied the moral and intellectual strength that defines true scientific pursuit. Living through 2 world wars, he remained a symbol of integrity, perseverance, and devotion to truth. When Germany descended into turmoil, Planck defended the independence of science and the unity of human knowledge. He believed that the search for truth transcended politics and nationality. Even after personal tragedies, including the loss of his son, he never abandoned his belief in reason, harmony, and the deeper meaning of the universe. His life became a model for scientists everywhere, a reminder that the pursuit of knowledge requires both intellect and character. The institutions he inspired continue to carry his name, from the Max Planck Society to research institutes around the world. These centers of excellence stand as living monuments to his vision, advancing the frontiers of science in physics, biology, chemistry, and beyond. They remind the world that curiosity and imagination remain the most powerful forces for progress. Every experiment conducted in those laboratories, every discovery made in the quest to understand the universe, is a continuation of Planck's journey, a testament to his belief that truth, once discovered, belongs to all of humanity. In the philosophical sense, Planck's legacy challenges us to reconsider the meaning of reality itself. The quantum world that he uncovered forces us to question the relationship between the observer and the observed, between energy and matter, between determinism and chance. The more scientists explore, the more they realize that Planck's discovery was not the final answer, but the beginning of an infinite quest. His work reminds us that knowledge is never complete, that every discovery reveals deeper mysteries waiting beneath. From quantum entanglement to dark matter, from information theory to artificial intelligence, the spirit of Planck's curiosity continues to guide exploration into new and unimaginable realms. His influence even extends into the realm of philosophy and spirituality. Planck himself believed that science and faith were not enemies, but companions in the search for truth. He often spoke of a divine order behind the apparent randomness of the universe, a unity that transcends human comprehension. To him, the quantum world was not chaotic but deeply structured, governed by laws that pointed toward a higher intelligence. His reflections bridged the gap between material science and moral understanding, reminding humanity that the pursuit of knowledge carries ethical responsibility. Today, every quantum computer, every experiment in particle physics, every exploration of cosmic radiation carries within it the echo of Max Planck's insight. The devices that power our world, lasers, transistors, and satellites, are silent monuments to his brilliance. Theoretical physicists still use his constant to measure the smallest possible divisions of space and time, now known as the Planck length and Planck time, scales so small that they mark the limit of physical meaning. These concepts define the very edge of what can be known, the frontier between physics and philosophy. More than a scientist, Planck became a bridge between centuries, between the classical and the modern, between certainty and uncertainty, between faith and reason. His influence shaped not just the field of physics, but the spirit of inquiry itself. The revolution he began continues to evolve, carried forward by generations of thinkers who see farther because of his vision. From the glowing light of black body radiation to the birth of quantum mechanics, and from the atom to the universe, Planck's legacy endures as the pulse of modern science. In the end, Max Planck gave humanity more than a formula. He gave us a new way to see reality. His discovery taught the world that even the smallest changes in understanding can alter the course of civilization. The universe, once thought simple and predictable, revealed itself to be subtle, layered, and full of wonder. Planck's legacy is written not only in equations and experiments but in the human imagination itself, a reminder that the search for truth, no matter how complex or uncertain, is the greatest adventure of all.